So the objective of this project is to analyze theoretically and experimentally the fall detection by using a Doppler radar. First, let me explain the principle of the continuous wave Doppler radar. So continuous wave Doppler radar. So continuous wave CW means we use a sine wave, okay, at one frequency. And the principle of this Doppler radar is the following. We have a source, so sine wave, that goes here, and then we will divide it. We will see y after that. And then it goes to a circulator like this. And then it goes to the antenna. And then it will be transmitted through free space. And you have the object that is moving. Let's suppose, for simplicity, it is moving with uniform motion, and it is playing like this, and it's moving with speed v. If the frequency that we send is f0, okay, f not here, so we send f naught. Because of the Doppler effect, we're gonna have the f frequency of reflected. Let's call it f. F over f naught will be 1 plus v over c over 1 minus v over c. And v is very small compared to c. So you can approximate that by 1 plus 2v over c. Okay. In other words, f equal f naught plus 2 f0 v over c. Okay. So this is what we receive, and because we have a circulator, when we receive the signal with the same antenna, it will go like this, and then we're going to use here a mixer. So the mixer will multiply the two signals, and it will multiply with the original signal that we have here. We can write it cosinus 2p f dot t, and the one we receive is cosinus here 2p f t. Okay. Here at the output we will have the multiplication between the two cosinus. So if this one is a and this one is b, you're going to have cos a, cos b. So this one can be writing 1/2 cos a minus b plus cos a plus b. Okay, so you will have the sum and the difference. The difference will be this one. The sum will be a higher frequency. So we're going to have here a low pass filter, and at the output we're going to have only the difference. So we're going to have something. So the amplitude is not important. It is the coefficient here, cosinus 2p f0 v over c t. So if there is uniform motion, we're going to receive a sine wave here, and the frequency of the sine wave is related to the speed of motion. But because the object is not plane and it can move at different speed, not uniform speed, we're going to have another kind of signal, which we call the radar signature of the moving target. So let's continue here. This is for the experimental part. For experimental part, we can design the Doppler radar by having all these different components, but we can also buy some modules available in the internet, and we will buy one. So the Doppler radar module, but we will need maybe to add the Wi-Fi module. So this one will be the radar. So we will find one, I think, at 24 GHz, and use one at 24 GHz. We will combine it with the Wi-Fi, and we also add the coax connector. And a box, we put that in the box. Okay, This is for experimental part. And then we will analyze with our Doppler radar for different person falling and doing many experiments. We will analyze the radar signature, so that in the time domain. And if we have the signals in time domain like this, we can use a Fourier transform using the time windows and analyze how the spectrum change with the frequency, with time. And based on that, we can also get the velocity spectrogram. So that will be for experimental mode. Now, how we're going to analyze this theoretically? So theoretically means we need to use Maxwell's equations. Maxwell's equation that's the main theoretical model we use for electromagnetic phenomena. Here we have a person that is, like this. It is falling, and we send a plane. Not sending a plane. Plane is just a simple model, an electromagnetic wave, and this electromagnetic wave will be continuous wave, so one frequency with a frequency f naught, and then we're going to analyze how the body will reflect this wave, and reflection, based on the reflection at one observation point, we can do exactly what we did here, but we can do it numerically. Okay, so we can use, for example, the Finite-Difference Time-Domain, FDTD. Why it is a good model? It's because it's based on the discretization of Maxwell's equation in space and time domain. So in time domains is good because we can have we can introduce motion of the objects. If you look to the literature, what is the main theory when you have electromagnetics and object in motion? The main theory that is proposed is based on Lorentz transformation, and this is what Lorentz proposed, and Einstein followed the same model, but Einstein added some new physical interpretation of Lorentz transformation. What is the principle of this Lorentz transformation? So it's based on a change of reference frame. If we have Maxwell's equation in one frame, for example, this one. So we're going to use the curls equations. So if we have the two curls equation of Maxwell's equation in one reference frame, to have it in the other reference frame, we will have to use in this model Lorentz transformation. So Lorentz transformation will change the space coordinates and time coordinates x, y, z, and time to another set of coordinates, so x prime, y prime, z prime, t prime, and the formula Lorentz transformation is for uniform motion. It's for the observer is moving from one reference frame to another reference frame, and you move, the difference between the two reference frames is speed v, uniform speed v. And you will have something with gamma. So gamma here is 1 over square root of 1 minus b square over c square. You have gamma here, and here you will have x minus vt. Here it's y, here it's z. If we change in the x coordinates, so it will change only x prime, and z prime will be z, and t prime will be gamma t minus xv over c. Yeah, I think there's no mistake here. So, but that's not very important. That's the principle. The principle is you are in a one reference frame, you will change the space coordinates. You also do change for the electric and magnetic field, E prime, H prime. was it E minus V x B V cross B, something like that. I don't remember the exact solution, the exact formula, but that's not important. So that's the principle. The principle is you transform the electromagnetic field, you transform the space and time to have the field in another reference frame. So the idea will be, for example, this is a body, but imagine this is one observer moving with V. So for that observer moving with V, you will use this Lorentz transformation to get the field at that position. If this is not observer but reflector, you apply Lorentz transformation to have the field at the reflector, and then you apply again to come back to the first reference frame. You have to do Lorentz transformation 2 times. But what happens if it is a body that is falling? You have many points. So for each point, you will get different time variable. You will have to transfer between different reference frames, but also each point doesn't have the same. For between the points, also you will have to do this kind of transformation. So this is not practical. It is actually not. It is impossible to apply this principle. This Lorentz transformation, what is called Lorentz transformation, are in reality they are auxiliary variables invented by Voigt in 1887. So the idea of Voigt at that time, he has the wave equation with an observer in motion. He gives you a certain wave equation which is a little complex to resolve, not like the wave equation with observer at rest, which is easy to resolve. The wave equation with observer at rest solution will be something like will have the form kx minus omega t. That's the form of solution we have for the wave equation. Either it is wave equation for sound, or wave equation for wave in water, or wave equation for transverse wave in electromagnetic field, in electromagnetism. So when the observer is not moving, the wave equation is easy to resolve. So when you have observer in motion in the equation is difficult to resolve, and Voigt use auxiliary variable, so variable of substitution. He substituted the space variable and the time variable in order to have the same form as the wave equation with no motion. And Lorentz used that, he found that interesting, in the context of Maxwell's equation. So if we look at them as a mathematical tool, they were useful at that time in order to replicate some phenomena like the Doppler effect or stellar aberration or other phenomena mathematically. But in the context of objects moving with complex motion, it becomes useless. And giving interpretation of this as being real change of space and time is also misleading. So we don't use this. So it's impossible to use this one for our problem. So we're not going to use that. So what is the method we're going to use? The method is the following. So we have the body that is falling, and this is the computational volume. And in this computational volume, we're going to use the Maxwell's equation, curls Maxwell's equation. Okay. And we will divide the time in time steps. So we will, during a certain delta t, we will solve Maxwell's equation for this problem. So we have the electric plane wave, and the body is not moving. So the person here is not moving. And for the next, so 2 delta t, next time between time frame, we can have motion. And this delta t, we can make it as small as we want. And you resolve the same Maxwell's equation. and we continue like this. That means we can consider, with this method, we can consider any object in motion. It doesn't have to be uniform motion. It doesn't have to be one observer moving. It can be many objects moving a different direction and with a non-uniform motion. So this is a method we're gonna use. We will compare our numerical simulation with experiments. What we will do in the experiments is we will video record when the person is falling. At the same time, we are saving the radar signature, and we will use a green screen, and the video of the falling person will be integrated in our FDTD simulation. Like this, we will have as much as possible close to what is happening in experiments, and we will compare in the end at the one observer. So what the observer will do, it will take the electric field received, mixed with the original electric field excitation, and using filtering, and then using the same principle we use for the Doppler radar. And then we will be able to compare the radar signature that we got from the FDTD simulation and the radar signature that we got from the experiments. The results that we obtain by experimentation are in agreement with the result that we obtain by simulations by using the FDTD method. So this shows that the method that we propose can be used for that kind of problem, electromagnetic problem, in the presence of objects in motion. So thank you very much for watching this video. Please subscribe, and see you in the next video.
Tu peux chuter.
Oh.